Today we are going to take a look at one of the exam questions in the Taiwan International Olympiad primary test. The URL is shown here, and there's an interesting question about a pendulum with mass m attached to a smaller mass m2 with a coil in between them. So let's find out the differential equation of this system. So here's the solution. So let's explore the problem from the thinking angle of forced simple harmonic motion. So the spring between M1 and M2 will exert a recoil force on M1. So take a look at the diagram again. There will be a recoil force from M2 acting on M1. And it is this recoil force that makes the equation of motion a little bit different from the simple harmonic motion. Now here, assuming the tension is T, then the vertical force equation is this one, and the horizontal force equation is this one. Let's eliminate T, the tension, with the assumption that theta is small, much less than 1. In this case, cosine theta approaches 1 and sine theta approaches theta. And the equation of motion simplified to these two. Eliminating T, we get this one. Now, back to the question. Now that we know the equation of motion of theta t, and following the hint, let's assume theta t equals to theta star t plus delta t, and that theta star t is independent of L2, and delta t is proportional to L2. So, and then let's go back to here, the solution. With theta t equals to theta star t plus delta t, and here we have this one. We plug it into it and expand it, and because delta p is proportional to L2, let's arrange all terms involving L2 to the right hand side and divide every term with L1. Here we got this expression. So the left hand side has nothing to do with L2, and the right hand side are all relating to L2. Now, because the left hand side is unrelated to L2, it must have a value that remains constant for any arbitrary value of L2. Let's pick L2 equals 0, and we have the first differential equation for delta star, which is this one. This equals to 0. And on the right hand side, it will become the second differential equation describing delta t. And here we see one more opportunity for vanishing one term, which is this term. It's because the L2 divided by L1 is much less than 1, and delta is proportional to L2, so this becomes a small object compared to the other terms, so we can get rid of it, and it's simplified to this differential equation. Seeing that M2 is small compared to M1, we can further simplify to this differential equation. And this equation looks strikingly similar to the differential equation of forced simple harmonic motion. You can take a look at what is forced simple harmonic motion here. And using this here, although it looks similar to forced simple harmonic motion, we still need to plug back the solution for theta star, which is this one. and then we put it back, and using the trigonometrical identities, we expand into this one. So this is a four simple harmonic motion with external driving force having frequency of either omega minus omega naught or omega plus omega naught. And resonance happened when the natural frequency of the simple harmonic oscillator, that is the omega naught, equals to the frequency of the driving force. So there are actually four driving forces here and two kinds of driving force frequency. One is omega minus omega naught, one is omega plus omega naught. But only the first possibility would yield a non-zero omega. Thus the resonance condition is omega equals to 2 times omega naught. Thank you.